Assalamualaikum warahmatullahi taala wabarakatuh and good morning. So this week our lecture is online lecture, which is a video recorded. Okay, this one motivation for all of you is not all things are difficult before they are easy. So chapter 4 is about elementary number theory and methods of proof. Okay, what is definition for direct proof? In order to evaluate the truth or falsity of a statement, you must understand what the statement is about. Okay. In other words, you must know the meanings of all terms that occur in the statement. Okay. So you are given this definition. An integer n is even if and only if n equal twice some integers. So n integers n is odd if and only if n equal twice some integer plus 1. So for n even, we have predicate here exists as k such that n equal to k equal to 2k. This is for even. For odd, exists k such that n equal k plus 1. Okay, k plus 1, so this number become to odd. So we have a statement here. Example, all the prime number are odd. Okay, this statement. For the hypothesis, number 2 is a prime, meets the statement. Number 2 is not odd, doesn't meet the conclusion. So as the conclusion, all the prime number are not odd. So 2 is the counter example. Okay. So use the definition of even and odd to justify your answer. Okay. So A is 0 even number. Okay. So 0, yes. Okay. The 0 equal to 0. So we use this one. K equal to 0. Okay. Because 2, 0. So this statement is true. Okay. Second statement is negative 301 odd. So we use which one? Okay. We can use this one because odd. Is it true? So we just replace the number. Okay. So 301 because we have 2k here. So we times 2. So negative 151 plus 1. So this is odd. Okay. Follow this theorem. Okay. Sorry. So negative 151 become to k. Okay, so we meet the definition here. N is odd, integer k such that 2k plus 1. How about the C? If A and B are integer, is it 2a square B even? Okay. So the same way, okay, we use this theorem. Okay, so we can come like this. So 2, 3a, 2b. So this is a k. So this is a k. So we use this theorem. Okay, we use this theorem. So it's true. How about D? If a and b are integer, then a plus 8b plus 1 odd. So the same way we use this theorem. So we can simplify this one to this one. So 2, 5a plus b plus 1. Okay. So this one can prove as a k. So we can use this theorem. Okay, can use this theorem. So true. Okay. Okay, how about this one? Okay, so the answer is yes, although the proof is not obvious because we don't know the integer. Okay, the integer 6 equal to times 3 is a product of two similar positive integers. So that hence 7 cannot be written as a product of two smaller positive integers. Okay, so it is only positive vector are 1 and 7. So a positive integer such as 7 that cannot be written as a product of two similar positive integers is called prime. So for the definition of prime, if n is prime, it's only if n greater than 1. So we can use this one for prime, this one for prime, this one for composite. Okay, so this is a theorem definition for prime number and composite number. Okay, is it one prime? Okay, so we go one by one. So 1 is no, because what? Because a prime number is required to be greater than 1 here. So now meet this definition. So the is 1 prime is no. Okay. The second one, this is a definition for prime. Is every integer greater than 1? Then 1 either prime or composite. Okay. The answer is yes. So let n be any integer that is greater than 1. So we consider all pair of positive integer r and s such as n equal to rs. So there exists at least two such pair, namely r equal to n, s equal to 1, and r equal to 1 and s equal to n. Okay. For C, write the first 6 prime number. Okay, this is the direct answer lah. Okay. First 6 prime number is 2, 3, 5, 7, 11, 13. Composite number, okay, 4, 2, 8, 9, 10, 11. It's not prime number. Try this one. Use the definition that given to answer following. Is 5 odd? Is n minus m composite for n greater than 2 and m greater than 1? And C is 2r minus 6 plus 10s is even. Try yourself first before you forward my video. Okay, for A is 5 odd, so the same way before. Okay, so we can simplify 5 equal to 2 times 2 plus 1. Okay, so 2 become 2k. Okay, so we can use this theorem. So, yes. Okay. Is it nm minus m composite? Okay, so composite, we use this one. We use n equal to rs. Okay, n greater than 2 and m greater than 1. Okay, so nm minus m equal to rs. Okay, because n equal to rs. Okay, where is r and s greater than 1? So n minus 1 equal to rs. So if we say r equal to n and s equal to n minus 1, so we get nm minus 1 equal to rs, which is s greater than 1. So by definition, nm minus m is composite. Okay. Okay, we go to the next example. Is 2r minus n plus 10 as even? So the same way, we simplify this question, we come to this one. Okay, come up with 2, so this one become to k. So we meet this theorem. So this is a true. Okay, counter example. Counter example, given a universally quantified statement, find a single example which is not true. Okay, it's not true. So this, we call it disproving a universal statement by a counter example. Okay, example, for all x, no Rx, where Rx means x as red hair. So we must find one person in the domain who has red hair. Okay. Next example, every positive integer is a square another integer. So the square root of 5 is 2.223, is not integer. Okay. So the counter example, actually the universal statement is for if exists as a member of D, the domain, such that Px is false. Okay. This is we call it counter example. For example, Px, every x is a prime number. Okay, for every integer x, but if x equal to 4, that is x is not a prime. So 4 we call it counter example to Px being true. Okay, proving existential statement. Okay, existential statement we use existential symbol. This is a general definition for existential statement. Okay, we can use two proof, constructive proof and non-constructive proof. Okay, one way to prove this is to find nx in domain that makes qx is true. So another way is to give a set of direction of finding such nx. Both this method we call constructive proof. Okay, we replace the value of x in domain. Okay, example here. These are two ways. We got this. Find x that makes them true. Give a set of direction. Example, there are integer number a, b, and c such that a square plus b square equals c square. So to prove, we just replace the value. Okay, we replace the value. Is times 60 come to 50. So true. Okay, so if we can find value of x to make this predicate is true, this one we call it constructive proof. Okay, example, some size, prove the following: existing and even integer n that can be written in two ways as a sum of two prime numbers. B, suppose that R and S are integer. Prove the following: existential and integer k such that 22r plus 8ts equal to k. Okay. So how to prove? For A, we find the n number. Okay? N value f. Example here, if n equal 10, so we got 10 equal plus 5 plus 5 or 3 plus 7. This is a prime number. Okay. So we can find the value of n to prove this predicate is true. The B, k equal 11r plus 9s. So then k is integer because it is a sum of product of integer. So we can k. Substitute 2k equal to times this one. Okay. A non-constructive proof existence involves showing either A, the existence of value of x that makes Qx true is guaranteed by axiom, true by theorem. B, the assumption that there is no such x leads to contradiction. This we call it non-constructive proof. Okay, for non-constructive proof, we have two ways. Show the existence of x is guaranteed by axiom or by proof by theorem. Second, show the assumption that there is no such x leads to a contradiction. Okay. Example here, show that there exists two prime number n and m that n plus m equal 18. Okay, we can replace the n number. Sorry. Oh, I cannot go back. Okay, disproving universal statement by counterexample. To disprove a statement means to show that it's false. Consider the question of disproving a statement of the form for each x in domain if px then qx. Okay. So showing that this statement is false is equivalent to showing that its negation is true. Okay. So how to disprove? For this one, we must make it this one false. Okay. We must use the negation of the statement. Okay. For this proof, by counterexample, okay, we must prove its negation like this. Okay, this is statement. Okay, conditions. This one statement. We have negation. Okay, its negation become to existential x, not px. Okay, this one we call it counter example. For example here, for each real numbers a and b, if a square equal b square, then a equal to b. Okay, so for solution, to disprove this statement, you need to find real numbers a and b such that hypothesis a square equal b square is true, and conclusion a equal b is false. Okay. So the fact that both positive and negative integer are positive square help in this search. So if you quickly see that 1 and minus 1 will work, or 2 and minus 2, we replace the value of a and b. We can see the statement and the counterexample, let a equal to 1, b equal to negative 1, then a square equal to 1 and b square equal to 1. So a square equal to b square, but a and b not equal, because 1 not equal negative 1. So we use this counterexample. We say this is true. Proving universal statement. Okay. A universal statement is generally of this predicate for universal statement. So use the method of generalizing from the generic particular. Okay, so the hypothesis Px is true. Also the conclusion is Qx is true. Okay, how to proving universal statement. This is a general statement, standard form for universal statement. Okay, use the method of exhaustion to prove the following statement. Exhausted, you replace the variable n. If n is even and this statement come true, then n can return a sum of two prime number. Okay. So we replace n here. Okay. N is even, so this even number. Sum of two prime number. This is a prime number. This n. This is a prime number. So we come to even number. So n if sum, prime number. Okay, plus prime number. So this prime number come to even. This prime number come to even. So this method, you just replace the value of n. Okay, this we call it exhausting. Okay. The most powerful technique for proving a universal statement is one that works regardless of the size of the domain over which the statement is quantified. It's called the method of generalizing from the generic particular. Okay, this one. Okay, you ask a person to pick any number, add 5 multiplied by 4, subtract 6, divide by 2, and subtract twice the original number. So this example to generalize from generic particular. This we call it about this one. Okay. Let's an empty box or the symbol extend for the number the person pick. So we use the algebra here. Pick a number. Okay. Add 5. So x plus 5. Multiply by 4. So this visual result. So x plus times 4 equal to 4x plus 20. Okay, and subtract 6, so minus 6, come to here 4x plus 14, divide by 2, okay, and subtract twice the original number. Okay, go to 7. So what is the method of direct proof? Okay. Okay, for the direct proof, this example for conditional universal. Okay, this is a standard form for conditional universal. Start the proof by supposing X is particular but arbitrarily choosing element of D, which hypothesis Vx is true. Okay, so we replace the domain. Okay, show that the conclusion Qx is true by using definition, by using theorem. Okay. Example, prove that the sum of any two even integer is even. Okay, how to prove? We use this theorem, this definition. Okay, we can try to replace for some pair for even integer, say 2 plus 4, okay, 6 plus 10, 12 plus 12, and so on. Okay. However, since you cannot possibly check all pair of even number, you cannot know for sure that the statement is true in general by checking it's true in this particular instance. So we no need to replace all because we don't know the infinity number. So many properties hold for a large number of examples and yet fail to be true in general. So to prove this statement in general, you need to show that no matter what even integers are given, their sum is even. Okay, so we can use this given it's possible to represent 2r because even is 2k plus 2s. So for some integer r and s. Okay, so by the distributive law of algebra, we can go 2r plus 2s equal to r plus s, which is even. Because we use the definition, even is 2k. So r plus s become to K. To support the statement to be proved, we are much complicated than this. So the method to use to derive a proof, actually we have 3 steps. Okay, first is formal restatement. Okay, for each integer m and n, if m and n are even, then m plus n is even. Okay, we restatement, okay, from the original statement. Okay, next is starting point. Suppose m and n are particular but arbitrarily chosen integers that are even. Okay, so we can suppose m and n are any even integer. Starting point. So the conclusion, okay, get to the conclusion. So the example here, the sum of any two even integer is even. That is a theory. Okay, so to prove, we use, suppose m and n are integer lah, particular, okay, even integer. So we must show that m plus n is even. Okay. So by definition of even, m equal to 2r and n equal to 2s for some integer r and s. Because we must, m is integer, m is even, n is even. M, because even, n is even, become 2k. So we use another variable here, r and s. Okay. So we replace m equal to 2r and n equal to 2s. Okay. So by substitution, we plus a two number of even, m plus m, so equal to r plus 2s. Okay. By factoring out of 2, r plus s. Okay. So let t r plus s, then note that t is an integer because it is sum of integer. Okay. So a conclusion that mn is even. Okay. Mn is 2t. Is a t, 2t, so t become 2k from the theorem. So it's even. Okay. For another exercise, example, for each n with n greater than 1 less than 5, n squared minus n plus 11 is prime. So how to use direct proof of a theorem? Okay, so if we replace the value of n, we got a 1 double, square of 1 minus 1 plus 11 is 11, and so on. Okay, so this is a prime. The prime is a prime number, is a prime number, is a prime number. So in each case, the resulting number is prime, so that the statement is true. Okay, so if we follow the 3 steps, okay, first formal restatement. So always try to write a formal restatement of the theorem you are trying to prove. Okay, we must transform the statement from informal language to logic. Okay, then the starting point, write down the things you are allowed to assume given the statement of the theorem. Okay. To prove a statement for each x, if px, then qx. Okay. So you need to, suppose x is an arbitrary object, we make px is true, and then show that qx is true. And the conclusion. So by this example, try by yourself how to make formal restatement, what is the starting point and conclusion for this predicate. For any integer n, if n is odd, then n square is odd. Okay, so how to formulate this statement? So for each x member of integer, so x is odd, then square is odd. Okay, from informal to formal. Okay. Second one, starting point. So our assumption here is x is some odd. So we use the theorem of odd is x 2k plus 1. Okay, this one for definition for odd. So since x equal to k plus 1, so x square, because we have square here, x square become to 2k plus 1 square. So we simplify this argument, okay, become to 4k square plus 4k plus 1. And therefore, we get it 2k square plus k. Then x square equal 2m plus 1. Therefore, x square is an odd integer. Okay, so odd. So we have to prove this predicate. Okay. This another example. Okay, write the first sentence of a proof, that starting point, and the last sentence of a proof, a conclusion to be shown. Every complete bipartite graph is connected. Okay, this one learn about the graph. Okay. The formal statement, we represent this informal into formal. For each graph, this is a domain G. If G is complete and bipartite, then G is connected. This is a conclusion. This is a hypothesis. Okay. So for the conclusion, to be shown just the conclusion of the if-then statement. Okay. The starting point, suppose G is a graph such that G is complete and bipartite graph. So conclusion is G is connected. So for the proof, the following shape. So we prove suppose G is a graph such that G is complete and bipartite, and therefore G is connected. So how to show in that existential statement is false? Okay, that we know that the negation of existential statement is universal. It's followed that to prove an existential statement is false, you must prove a universal statement is true. Okay. Example here, there is a positive integer n such that n squared plus 3n plus 2 is prime. Okay. So how to prove? Proving that the given statement is false, equivalent to proving its negation is true. Okay. So the negation for this statement is for all there is become to for all positive integer n squared plus 3n plus 2 is not prime. Okay, so we follow that theorem before. So because the negation is universal, it is proved by generalizing from the generic particular. So how to prove this statement? There is a positive integer n such that n squared plus 3n plus 2 is prime is false. So suppose n is any positive integer. Okay, we must show that it's not prime. Okay, we can factor n squared plus 2n plus 2. We come to this one by factor. Okay, so we also note that the n plus 1 and plus 2 are integer because they are sum of integer. So that both n plus 1 greater than 1 and plus 2 greater than 1 because n greater than 1, thus n squared plus 3n plus 2 is a product of two integer each greater than 1. So it is not prime. This one you must refer to definition for prime. Okay? This one for prime. So as we follow this definition, this statement is not prime. Okay. So another example, disprove universal statement by counterexample. For this, use this theorem and prove that this one. Okay, so we must prove that n number of integer n squared plus 3n is even implies n is odd, is 4. Implies that means this symbol. Try by yourself first. Okay, prove that n member of z n plus is even implies n is odd is false. Okay, so we can try replace n is equal to 2 and get that n squared plus 3n equal 4 plus 5, 60 is even. So we have a counterexample to the contrapositive. Okay, so we find a counterexample n equal 2, we do the job, we got it, 60 is even, but n equal to is not odd. Okay, so we prove this statement. So this will call it disproof by counterexample. Okay, conjecture, proof and disproof. This one for your knowledge about conjecture. Okay. On the basis this experience, you can formulate a conjecture. Okay. If P is true, then we call it conjecture. If P is true, then Q is true. However, you need to prove it by applying some deductive reasoning. Okay. When it's proved, the conjecture becomes a theorem, or you can find counterexample to disprove the conjecture as case in which P is true but Q is a false. Okay, so to prove that a conjecture is true, you need to prove it is true in all cases. To prove that conjecture is false, you need to provide a single counterexample. Okay? So counterexample is an example that shows that conjecture is false. Okay. So this one a step to make it a conjecture. Find a pattern in the sequence that you are given or write out example to find a pattern. Then write the pattern that you have found in the form of a conjecture. If given a conjecture, find a counterexample to prove that it is false. Example here, for every n power of 3 is positive. Show that the conjecture is false by finding a counterexample. So what is the value of n to make it this counterexample? Try by yourself first. Just replace the value of n. Okay, example here, if we replace n equal to 1, we got n power of 3 is 1. So 1 greater than 2. Okay, this is the true. If we replace n equal to minus 3, we got it n power of 3 is minus 27. Minus 97 is less than 0. This become false. So n equal to minus 3 is a counter example. Next example, to potential the sum of the first and odd positive integer. Okay, so we look the pattern, we replace the pattern. 1 plus 3 equal to 2 square, another number square, so we got the pattern. We call this the sequence pattern. So the sum of the first and odd positive integer is n squared. Okay. So next, finding a counterexample. Show that conjunction is false by finding a counterexample. For all real number x squared is greater than or equal to x. Try to find the counterexample. Okay, here we can, because of the real number, so we can replace with a real number here. Example 0.5 equal to 0.25, and 0.25 is not greater than or equal to 0.5. It is that, in fact, any number between 0 and 5 is a counter example. But not every conjunction is known to be true or false. Okay? Conjunctions that are not known to be true or false are called unproven or undecided. This example. Okay. Whereas many even number greater than 2 can be written as the sum of two primes. Okay. So this problem said no one has ever proved this conjunction is true or found a counterexample to show that is a false. This example for unproven conjunction. Okay, this is about conjunction, proof and disproof. Okay, this is another example. Okay, it's about what this one? The last one. For example, proposed in the 18th century that A power of 4 equal to the is A power of 4 plus B power of 4 plus C power of 4 equal to D power of 4. F no non-trivial whole number solution. Okay, in other words, no three perfect fourth power add up to another perfect fourth power. Okay, this is an example for proven conjunction. Okay, that's all for the chapter 4. It's about theory of number and the method of proof. Okay, so after this you refer to Oceania for the exercise for this chapter. Okay? You have 3 questions to disprove and prove. Okay, these first questions about disprove the exist an odd integer n such that n squared plus 2n plus 3 is odd. Okay. The second exercise about to prove the predicate. And the third one. So just refer to Oceania and please upload the answer for the exercise in PDF. Okay, that's all. Thank you.